My name is Jack Moran. I am the Senior Director of Cable Access Networks Research, and I've been in the industry collectively in cable for over 20 years and telecommunications for almost 40. In my present capacity, I was hired by Huawei to meaningfully forward the work on DOCSIS 3.1 in the distributed CCAP. But let's give a little background for you on cable in general. Cable TV has been in the data business, the data transmission business, since about 1996. If you count some proprietary non-DOCSIS standards, there were early data systems around 1995, but it's pretty much starting 20 years ago. As time went on, they realized they needed more bandwidth, and the initial systems were quite primitive and pretty slow and worked well regardless if the system was maintained or not. As the modulation rates get higher and we suddenly realize, geez, what can we do as a vendor to survive some of the impairments, and what can the MSOs do as a community to improve the networks, the evolution was on. DOCSIS 2.0 came out in about 2001, and that was the first real birth of the modern technology where they had two standards, SCDMA and ATDMA. Both could work up to, 64 QAM. Before that, 16 QAM was the highest. And they could also double the symbol rate, so the data signaling rates dramatically increased for DOCSIS 2.0. But still something was missing, so they decided, well, let's do DOCSIS 3.0. The biggest difference between DOCSIS 2.0 and 3.0 is fundamentally the concept of bonding many transmitted channels logically together as one bigger data pipe. So where you might only have got 38 megabits on a single channel, now you could get 200 or 300 megabits downstream to a single customer. Bonding upstream also was introduced. It didn't roll out as fast. The standard started in 2006, and I believe it wasn't until 2009 that the first real bonded upstream systems appeared. So the throughput was changing all the time. In those early days of cable, upwards of 2009, the whole industry was on track with Moore's law of growth and bandwidth expanding. And then suddenly the bubble hit, and a lot of the bandwidth projections, particularly in the return path, didn't come to foil. So ironically, bonding was used primarily to make sure the upstream, to make sure the downstream bonding was fast enough for various over-the-top services. Enter 3.1. With all the pressure from the optics side of the house offering competition to the cable operators, they needed to come up with a more robust modulation, and so they looked no further than LTE. So if you look at it, all DOCSIS 3.1 is it's left the single carrier concept and gone to a multi-carrier, sub-carrier FFT transmitted bandwidth. Downstream, it is OFDM, and the basic channel is 192 megahertz wide, of which 190 is made. There's a 1 meg guideband on each side. So the concept is someday they'll support up to 6 of those carriers downstream, and at a 4096 modulation rate, no less, that would put the throughput well over 10 gigabits downstream. Upstream was a little more complex. Bandwidth is not nearly as much. After all, you have today only 42 meg or 85 meg is now coming out common in the US, and even all of Europe and the rest of the world is only 65 megahertz. So that's sort of limited on your DOCSIS 3.0 upstream potential of roughly 150 to 200 megabits per second, with 85 3.0 increased to about 350 megabits a second. That 85 megahertz for DOCSIS 3.1 is 500 to 700 megabits, so it's a substantial increase in the return path. This will allow the operators to probably or possibly offer symmetric services, which has been a big key point of contention with some of the optics companies' challenges. So a couple of hundred megabits symmetrical, I think, is very possible. A gigabit symmetric, not possible until the return path is extended to 204 megahertz, and the forward path is extended maybe even past 1.2 gig. With that said, the strengths of 3.1 over previous standards is its noise immunity is far better because it's using low density parity check for error correction. So roughly several dB improvement over the Annex A or Annex B of ITU that we use today for either in America, North America, Annex B, or Europe and the rest of the world, Annex A. With that said, that additional margin allows them to get a couple of data rates higher, and with the data rates and the narrower band subcarriers, equalization is much simpler now. It's usually a one-tap equalizer for each carrier. After all, it's only either 25 or 50 kilohertz wide. With that said, with this longer symbol rate, OFDM, and in particular upstream, OFDMA, is on par to the noise immunity that the SCDMA almost never used in DOCSIS 2.0 provided, since OFDMA is mandatory in 3.1, it is no longer optional. It will be used by everybody. However, as was the case in DOCSIS 3.0, we had a transition period, which we'll call a hybrid mode, which all DOCSIS 3.0 work bonded down but no bonding up. It allowed to stay 2.0. Well, they've now made that decision for 3.1. Even though it wasn't originally in the standard, the MSOs all agree, let's do a transition period. So there'll be what is called a DOCSIS 3.1 hybrid mode, which will be 3.0 up, 3.1 down. Huawei, on the other hand, since we believe in technology, have from the very beginning have done OFDM down, OFDMA up, and now because they've asked for the hybrid mode, we've implemented that too. But the truth of the matter is, the greatest potential for 3.1 is a pure OFDM both ways. The promise of OFDM is if certain parameters in the network are improved upon, the real potential, extremely high data rates, extremely high throughput can be acquired or achieved. Today, DOCSIS 3.1 will work in 100% of the networks worldwide. Having said that, no guarantee what that throughput will be. It'll be all over the map. Certainly DOCSIS 3.1 has a lot of knobs to turn. It can do a lot of flexibility, and so you're going to see a wide range of throughputs reported depending on whether the MSO is taken upon himself or herself to actually address the network in the three major areas of issues that must be resolved. I will name the issues and we'll discuss them. The number one issue, it's not even a secret, it's the elephant in the room no one wants to talk about. The weak link in all, I mean all, HFC systems is actually the analog optical transport downstream and the optical analog transport upstream. They are dramatically lower in performance than the amplifiers in the coax system. The second major problem, which no one ever wanted to talk about, is a simple little thing called RF combining networks in the head end of the hub. When the bandwidth was narrower, say 750 or 860, you could take a two-way splitter or an eight-way splitter for granted of having a certain frequency response. They found out when they went to 1.2 gig that was not true. And in fact, many IC caps of today transmitting at a gig have over a dB of ripple in band caused solely by the combining in the head end. That dB of ripple cannot be fixed by the IC cap. It must be fixed by the modem equalizer. Now, the good news is the modem equalizer can do that and still work, but it took away from margin it might have had for other impairments. Nothing's for free. So if you go to a distributed C cap, you eliminated both of those problems in one shot, namely the RF combining and the nonlinearity in the analog fiber is all gone because it's digital fiber to the node. Finally, the third major problem that is an ongoing problem, every network in the world has it, some worse than others, is poor grounding techniques within certain countries, and therefore noise couples in everywhere. Now the good news is OFDM has a long cycle period, so it has pretty good immunity to the transient noise that's happening, and it has outstanding immunity to ingress noise. The reason for the outstanding immunity is because if you have a narrowband ingressor that's very high on power, you just don't transmit that carrier at all, or you lower the modulation to where it handles it fine. Again, think of it as a toolbox. All the knobs you can turn one way or the other that makes this thing work like a champ. Now, on the upstream, this is where these return path problems lie. There was a second problem because of that optical linear path again. When the noise gets too high, these ingress noises or even some impulse noise gets too high, it clips the laser. The DC cap, and particularly the Huawei DC cap, is about 15 dB more headroom than the optics. So we will not ever clip from noise that we've measured in any network. Simply put, we have a shot of supporting 4096 upstream. That's the maximum data rate upstream. In the analog fiber nodes today, they're pretty much resigned to the fact that 1024 QAM is going to be their upper limit. So there is a real payoff by distributing out to the node in long-term throughput. Again, when they're ready to do that, the long-term end game, I don't think there's much argument that's what'll happen. But having said that, you have that trade-off, and on the downstream, same thing with the nonlinearity of the optical transport and coupled with 960 megahertz of bandwidth. They're lucky if they get 43, definitely no more than 45 dB MER. The DC cap, we're guaranteeing 54 with that same bandwidth at the output. That's a real world gain, 1 or 2 data rates higher. So what I'm saying is, when you go to a DC cap, you're assured that you're giving the network and the modem enough margin that even if they're not ideal, they'll still be able to run error-free 4096 QAM. Today with an analog fiber, that is not true. It's taken almost all of it away. So if you talk to most MSOs, they'll tell you their goal initially is 1024, maybe as a push 2048. They're not thinking too many 4096 unless it's a very, very small node. That's not an issue again, like I said, for DC cap. So that's the evolution, the technology going, extending it out to a DC cap or even a remote PHY, as you've heard. That is a digital out to the node. Only difference between a DC cap and a remote PHY is all scheduling is done at the head end, so the delay all the fiber to the IC cap in the head end has to be taken into account. There is no delay. Advanced mapping you need to do for the DC cap. I mean, heck, a couple hundred nanoseconds, not much more. It's a very small amount. So we expect a better throughput play, particularly on what I perceive younger people will notice. I believe the DC cap will be the architecture of choice for gaming, where that latency comes up big time. It's almost not even the speed, it's the latency. Anyway, all the cable operators have chose 3.1 to compete. I believe they can. Certainly it'll extend the life of the coax plant longer than they thought, even while they make the coax plant better by making the nodes smaller, less cascade. Yeah, the numbers I've thrown out assume certain things that are progressing over time. The cascades are getting smaller, etc. And then finally, because again, Huawei does believe in innovation, the fact that we actually do 16K QAM. Now you need, really, realistically speaking, at least 51 and maybe preferably 54 dBMER to run error-free. So that immediately eliminates the thought of analog fiber, and that will never happen. DC cap with an M+0 and maybe an M+1, I think has a good shot. The reason I can't tell you more than that now is while the DC cap can transmit, and we've already demonstrated that at Cable Labs, we had to use a vector signal analyzer to demodulate it because there is no modem that exists that works at 16K QAM. Would they in the future? I guess the market will decide that, but certainly there'll be cost factors to be dealt with. We, on the other hand, know that we had the horsepower, we had the intelligence and the capability to deliver it now. So we intend to use, at 2MSO suggestion, 16K QAM for a totally different reason you may not have thought of. Test equipment. Take a 24 megahertz slice of bandwidth, put it in an area they're not using, and just run it and see what you record. You know, we can put test equipment out there, even on the network, that'll measure the 16K QAM, because if anything is out there, and I mean anything, nonlinearity, phase noise, interference, crosstalk, you won't get 16 kQAM. So it's a way of them evaluating way ahead of the fact without impacting customers. Can they actually dare to increase the throughput to the holy grail, as we call it, 16 kQAM?